So we've looked at how we can attach an LED, which requires 20 milliamps or 30 milliamps or even 40 milliamps to drive. However, what if we want something more than that? We want 100 milliamps, we want 200 milliamps, we want an amp, we want 10 amps, okay? So now we need to look at how we will do that. And the device we're going to use is a FET, more specifically a MOSFET, okay? And there are a couple of really important things about MOSFETs. The most important thing is that there are logic MOSFETs, okay? Now logic FETs, and I'll just highlight that, logic FETs are designed to be driven by low voltages as used in microcontrollers. You know, anything from down to like, 2 volts or something, or a volt perhaps in some cases, right up to 5 volts. But many MOSFETs are designed to be driven by 10 volts. Okay, so when you're looking for a FET to connect to a microcontroller, that's the first thing you need to look for, is a logic FET. Okay. Now there are other types of transistors. You could use a BJT transistor. There's JFET transistors. There's all sorts of different transistors nowadays. I'm just going to look at this particular logic MOSFET and have a look at a couple of these different models. Okay. So what we've got here is we've got a small what we call a TO92 plastic case. This is a very small device. You'll see, looking at the capabilities of it, that it can handle 60 volts. When it is on, it has a resistance of 5 volts. We'll look at this. 75 milliamp current, okay, and continuously rated for 200 milliamps, okay, but we can pulse it for short periods of time up to 500, right, as long as we don't exceed the power dissipated by the device, which means the internal resistance of the device doesn't get more than 1 watt power across it. So let's have a look at the actual device itself. What we've got is we've got a gate, and we've got a drain and a source, okay? And what we've got here is we've got an internal, the structure of the MOSFET creates this internal sort of diode here. And the idea is that we apply a voltage to the gate of a certain voltage, and this will then turn into a conductive path of a certain low value resistance. And in this case, it will be no more than 5 ohms. It'll probably be less than that, might only be about 2 ohms or so, but it will be a couple of ohms perhaps, and but no more than 5 ohms. So again, we can look at this in terms of our equivalent circuit, and it's quite a nice, tidy little equivalent circuit here as well for the sort of use we've got for it at the moment, okay? So really, the resistance of our equivalent circuit is infinite. And that's sort of shown by the fact that the gate here is not actually connected to these terminals inside. In fact, there's a tiny little layer of insulation between them. So basically, when we apply voltage here, we create an electric field inside the transistor, which causes the channel here to close, okay? Now, that channel, when it closes up, will have this RDS, the drain source resistance, in series with it. And that's what we're showing here, really. We've got a switch and an RDS, a series resistor. And this is, yes, it's a fairly basic model. There are more complex ones, but at this stage, we're thinking this is fine, actually. We're just going to look at this as simply a resistor, and we've been told that it is 5 ohms. So let's have a think about this. Let's say we've got 12 volts here. And this is a 6 watt load. So a 12 volt, 6 watt load, that's sort of like a bulb on the inside of a car. Now, the power is 6 watts, the voltage is 12, that means the current is ½ an amp, okay? And RDS is 5 ohms, so that means that we have got ½ an amp flowing here through the circuit. So we'll go through conventional current, half an amp. And what that means is that the power dissipated inside this device, that's inside this little plastic device here, is going to be I squared R, which is 0.5 times 0.5 times 5, which equals 1.25 watts, which exceeds the total power dissipation of 1 watt at 25 degrees Celsius. So if we got any warmer, then this is actually, not at all suitable. So we can't do this. This won't work. Okay. So let's just have a look at that and think about it. Let's have a look at another FET. It's exactly the same symbol, gate, drain, and source. There's the connections for it if you're going to use one. This one here has got a 60 volt maximum operating voltage. That's fine. So did the other one. Okay, this one here has got a continuous rating of 32 amps. The previous one had a continuous rating of 0.2 amps. So this significant difference here. And this, you'll notice these higher power packages, what we often term as TO220, is this particular package with the legs which get soldered into holes in the circuit board. We can pulse this, well, this one here, we can pulse at 128 amps. So that means if we're doing some short duration pulses, 32 amps is fine, but actually we can go to 128. Now, just remember though that as the temperature increases, we will, we have to derate this, which means we have to have less current through the device. Now, here's something that wasn't in the other data sheet, and that is the voltage that is required to turn this device on. And at least 1 volt is required to turn it on. And any device no more than 2.5 volts will be required to turn it on. So using it with our 5 volt circuit is fine. Now, this is the really interesting, what is the on resistance? Now here you have a look at, typically it's 0.035 ohms, so 35 milliohms, whereas this one up here was 5 ohms. Now that means that we can have considerably more current through here without it generating a great deal of heat. Okay, again, we've got an infinite input resistance. Now the fact that these have got infinite input resistance just means that they represent no load for our microcontroller. So we can connect it to the microcontroller without any problems at all, okay, nearly. So when we connect it to the microcontroller, we can do it without this resistor. And you often will see these sort of circuits where, if you look around online, the output of the microcontroller is connected straight to the FET. Now, there's a reason I don't like this, and it's not recommended always, is that when your microcontroller is powered up, every single I/O pin is configured as an input. And that means that there's a very high resistance here, which means that this line here could actually float. So for a short period of time, when your microcontroller is powered up and your circuit is powered up, this is actually possibly floating, which means that it could turn on the FET and then turn on your load. And then as soon as this is turned into an output and turned off, then this would actually turn off the load. But you would get, and you could get instantly a triggering of the load here. So what we do is we often connect a high value resistor here so that the point of this line here cannot float ever, okay? So let's look at the equivalent circuit here. What we've got is an equivalent circuit. So we already have worked out that this is around 26 to 30 ohms, depending on the temperature. We've got 5 volts as our VCC. We've got an infinite resistance here, but we have connected a 10k ohm across it, which means that the voltage at this point, V out here, will be slightly lower than VCC, but in actual fact, it won't be much lower at all. 26 ohms compared to 10k, well, that just means that this is going to be a little tiny bit smaller than VCC. Okay, so that means that we're still going to get enough voltage to drive our FET. Okay, right. So let's have a look at a couple of examples. And this one, say we connect 150 milliwatt load here. Well, there we go, 12 volts, the load's 150 milliwatts. The current is 0.15 over 12, which equals 0.0125 amps, okay? So that's now our limit for this device here, this 2N7000 device. Our continuous current limit for that was 200 milliamps. And with this load that we've connected, we've got 12.5 milliamps, so that's fine, okay? Now, what is the maximum, what is the voltage, the VDS? So the voltage between the drain and the source, this is the maximum voltage. If you go much higher than this, well, actually our VDS rated for this is no more than 60 volts, and we're only using 12 volts. Now, of course, that 12 volts will appear across this device when it is turned off. This electric potential here will appear at this point, and this will then have 12 volts across it, okay? So that's why we don't want to go any more than, well, our maximum is 60 volts for both types of FET, actually. Now, the power dissipated by the FET, so the current, which is in this load here, we've decided that it's 12.5 milliamps or 0.0125 amps. So 0.0125 amps times now RDS. I'll call it, oops, there's a little mistake there. That's the RDS for this FET is 5 ohms. So that means that this is 0.125 squared times 5, which is really 0.78 milliwatts. Okay, so it's very small amount of power dissipated by our little plastic package. Okay. Now say we want to increase it to the high power one. We want to change to 150 watt load. So we're talking about very high power here at 12 volts. That's 12.5 amps. So we've got 12.85 amps now in this circuit. So 12.5 amps. The voltage is 12 volts, and of course that's fine because we've got a 60 volt rating up here. And the power dissipated by the FET, well, here we have 0.035 ohms or 35 milliohms is our on resistance. And of course that works out at 5.5 watts dissipated by the FET. So that's actually, that's well within its rating. It can handle 32 amps continuously. It doesn't give us a power rating, it gives us an ampere rating. And up here, we don't get an ampere rating. Well, we do get an ampere rating of 200 milliamps, but we get this dissipated power, which we're not allowed to exceed. So this is how we would connect a high power load to the microcontroller. Straightforward, except for one situation, and that is where this load has an inductive component. Okay, so for instance, like a motor or a solenoid. And now this particularly, I'm just going to just tidy up this because I think that's how it is in the notes. So let's have a look at these inductive loads. So what we know about an inductor is that when there's current in an inductor, there's a magnetic field which is built up around the inductor, and you can work out the size of this field. But what happens when you take away the energy source is that this magnetic field still exists around the coil of wire that you've got, and that happens, then it's got to go somewhere. So if it's got a path, then it will actually, the field will collapse back very quickly into the coil, and that will create current. Okay, now let's just have a look about what that means in terms of our microcontroller. So as our microcontroller is on and our load is turned on, then the current will flow in this direction. And because this is a load, the voltage polarity across a load is in this direction. So this is positive and this is negative comparatively, okay, in terms of voltage. So that's fine. The conduction is okay. Now you'll notice that I put a diode here, and there's a built-in diode here as well as a side effect of its manufacturing process. This diode will not be conducting. Diodes conduct in the other direction. So this diode is here to conduct if the voltage ever swaps. And that's exactly what happens when we turn off the FET. The source voltage is taken away from the coil, but of course the magnetic field collapses and starts to drive the current in the same direction as it was going before. But of course now what you've got is you've got a source, not a load, which means that the voltage is actually in the opposite direction as well, because the voltage and current are in the same direction in a source. And what that means then is that we've got current, we've got a voltage in this direction here, and this point here then becomes negative with respect to 0 volts down here, and the current will actually conduct to ground through the diode. Now that's because this point here becomes negative very rapidly, okay? These diodes need to conduct a lot of energy when this happens, and you'll find that special types of diodes called Schottky diodes and high power ones are used for this purpose, okay? And so that's okay for a small circuit. We could possibly rely on the built-in diode of the FET, but that's not very good. So really what we do is we connect this diode here. And of course, now our voltage is in the opposite direction. The voltage will then cause the current to flow back around this direction here, and it will not go to the FET, and it won't damage it. So this flyback or flywheel diode is critical for inductive loads, okay? Don't try to build one without a diode. It won't, your FET won't last long. The voltage across the FET can easily rise above its maximum, which is 60 volts, okay? Even though this is 12 volts, this voltage spike here can be perhaps hundreds of volts instantaneously, and that will cause the FET to die a ungraceful death. And because it is connected to our microcontroller, the pin of the microcontroller will also die an unnatural death. So there's very low risk in this situation. This is really important, that these diodes, and you've got to just think, well, if you know about diodes and you've learned about diodes, you think, well, actually it's in the wrong direction. Well, it's not. It's actually in the right direction for when the load is turned off. The current will try and continue to flow. The voltage will swap polarities because of the nature of it turning from a load to a source, and therefore the current will flow through the diode and not through our FET. Don't rely on this internal FET of the internal diode of this FET for much protection, okay? So that wraps up the ideas around connecting devices, and there's really only one little section left in the course, and that is just a general comment about what you've learned so far, and that's really that we've looked at how hardware and software work together inside a microcontroller, the fact that a microcontroller inside an embedded system is an automaton, and that has got to be reactive and responsive to the environment because there is no human input often to many of these devices. You know, they sit inside your washing machine without you monitoring them. They sit inside and they monitor air pressure and do all sorts of things in your cars, control the fuel. And really what you need is you need to develop this sort of eyeball understanding of what a microcontroller and an embedded system offers to your designs and for solving programs in the future. And that means actually choosing a microcontroller for a project that is appropriate. We have a saying in English not to use a sledgehammer to crack a nut, use the right tool for the right job. And that goes for choosing a microcontroller for an embedded system at all, because we don't want to waste money on more expensive parts than they're actually needed. This is costly decisions for manufacturers. You don't go and buy a $5 part when you need a $1 part and you've got to manufacture 500,000 of these devices, okay? It goes, you'll profit pretty quickly. And there are many different features in the microcontroller for you to choose from. And I've just listed a number of these here. The microcontroller can run at different speeds. In fact, the AVR is limited to about 20 megahertz, but there are other microcontrollers that can run much faster. So if you need a faster processing speed, then buy a microcontroller that will work at a lot of higher speed. The power supply connections, typically these devices run off a battery or some sort of power supply. If you're running off a battery, then the really important thing is power consumption. And it's been able often to put your microcontroller into some form of reduced power or sleep mode. The package that microcontrollers come in, they vary significantly. We mostly use these surface mount devices, QFP, or one of those other similar sort of surface mount devices. Not so much often in designs would you see a dual inline plastic, the bigger package used anymore. Okay, and of course this means that things can be much smaller. How much they cost and how many you need. Now, another really big consideration there is if you're doing multiple projects using microcontrollers, then it might be easier to buy 1 million microcontrollers of one type than it would be to buy 750,000 of that type and 250,000 of another. But of course it might not be. And so an engineer's job is often to balance and weigh up these ideas, and then it comes down to designing things around, like for instance, the size of the calculations that you might have to do. You might be doing 8-bit, 16, 32, or 64-bit calculations, and 32-bit microcontrollers are very common nowadays. Okay, and certainly if you increase your speed, then you might be able to do floating point calculations fluidly and easily on the fly. And some microcontrollers, of course, have got things like floating point processors built into them to do that sort of stuff. How much memory you need, how much data processing memory you need, how much program memory you need, and whether you need to store any non-volatile data between times when the unit is powered on and powered off. And you'll find that that EEPROM is very common in devices nowadays, where you'll take your car in to get a service, they'll connect up their controller to it and they will tweak the settings inside EEPROM for the microcontroller. They won't re-flash the microcontroller with new software necessarily, but just tweak its settings in EEPROM. How many I/O pins are needed for your particular embedded system, and how many things you have to connect to it, and how many ADC channels you need. What are the DC characteristics? Now, we've looked just now at the DC characteristics and how the internal resistance of the microcontroller for its output pins is quite important for you to understand. How many external interrupt pins there are, how many timers there are. Now, another really huge consideration is the support for developing these sorts of things. And that's the tools that you use, like we've got Atmel Studio. However, there are other more proficient tools for some other environments as well. And in fact, there are other tools for the Atmel which are very common. Code Vision, for instance, is another tool for the AVR system. What libraries are available? Man, if you're going to connect a particular interface to a microcontroller and someone's already written the library for that, that can save a huge amount of time for you, okay? Being able to debug a microcontroller while it's running in a system is hugely important, and the AVRs have some capability. They have a one-wire debug model which you can use. Other microcontrollers have other more sophisticated features as well. Your supplier. Okay, now just a couple of years ago, Atmel sold to Microchip, who have the PIC range, and there was a bit of worry about whether the AVR microcontrollers will continue. But Microchip are committed to both the PIC range and the AVR range because the AVR has such a large market support. Okay. Now, another really important thing is your intellectual property. When you write some software and put it inside a microcontroller, are there features that allow you to protect that code so that no one can read it back from the microcontroller? And the AVRs have this sort of facility. Whether there are other features built into it, like we've got a UART, or in actual fact, of course, we've got a USART, Universal Synchronous Asynchronous Receiver Transmitter, but there are other device types built in, I2C, one wire. Some microcontrollers have these features, some have more features, different features. Another really important thing is the fact that our microcontroller is very susceptible to what we call brownout, which is when the power might be sitting steadily at 5 volts, but actually it can dip in for a very short period of time just to a low voltage, and that can upset the processing of a microcontroller significantly. And so there's a brownout detector inside the AVR we haven't looked at, but what happens then is if the voltage reduces instantaneously, if it goes below a certain value, then it will reset the microcontroller and start its programs from scratch again. So, and we've also got the watchdog detector, which you've learned about in the assignment. So, you know, you should be able to understand many of these things, find detail about them. It's not remembering everything. What it is it's all about understanding this stuff and thinking really clearly about what it is that we are looking for. We are looking for an automaton that is reactive and responsive to its environment. And that is a hard thing to meet sometimes. And so I just implore you to engage with microcontrollers, build some projects, and have a great time using them. Cheers. Thank you very much. Bye.